So let's take a step back. I woke up this morning and it was 2017, which is really weird. Yesterday, my dad called me on the phone and said, hey, there's this article in the New York Times about artificial intelligence and the job market. Do you have anything to do with that? I was like, yeah, you'll never guess what, Dad. I've been working in this for like decades. This is right up there with when he asked me if I knew anything about big data. But anyway, the fact that articles like the one in the New York Times yesterday around AI and machine learning are really sort of in the popular minds now is new, right? I remember 15 years ago writing a paper, trying to figure out, okay, how can I convince the world that a tweak to a nearest neighbor algorithm that's going to run on a UCI data set with like 700 data points is important in any way? Like, well, okay, well, maybe the first paragraph of the paper shouldn't be about a 700 example UCI data set. It should be about, well, in the future, we're going to be able to like solve cancer or drive cars or help people order food or do security applications or help people communicate, all this sort of pie in the sky stuff, and here we are. This stuff actually happened. It's really weird. And also it's really mission critical. Like, this technology is no longer stuff that we use just to write papers or to make ourselves feel smart or to think about what might happen someday tomorrow if everything we think will work actually works. These are systems that now people rely on every day without even knowing it. And that's interesting and a little scary. So I've been at Google, 9-ish years. For most of this time, I've been working on machine learning systems. Some research, some making sure that these systems work well every single day, every single minute. Turns out to be an interesting job. And in this role, I've come to appreciate the phrase technical debt. So for folks who've heard of technical debt as a phrase before? Okay, cool, great. So we got about a 50% hit rate. When I first gave this talk at NIPS a couple years ago, I got maybe 1 or 2 hands, and maybe introducing the word technical debt to the machine learning community was a useful service at the very least. But let's talk about technical debt. It's a framework from the field of software engineering for thinking about how to account for the costs of moving fast. And oftentimes it's really appropriate to move fast. Maybe we have a deadline to meet for a research conference. Maybe we have a product that needs to launch by a certain date. There's very good reasons for moving quickly. And the point here is not that incurring this technical debt when we're moving fast is bad. The point is that if we don't pay down technical debt, that over time, those costs will increase, they compound. So this is very much sort of an economic metaphor. I need to point out it's not a metric. If you ask me to measure the technical debt in your system, I'm unlikely to come back with a strict dollar value. But as a metaphor, it's extremely useful. So let's think about some things that increase technical debt. Well, if your system is not well tested, either in the sense of unit tests or system tests, like that's probably going to increase technical debt over time. If your system is very complex, all kinds of little spaghetti pieces all over the place. If there are a large number of dependencies or entanglements with other parts of the system. If you have poor code readability or poor documentation, this will tend to increase technical debt. There are a number of design sort of anti-patterns. Cool people call them smells if they talk about a smelly system or smelly code. None of these things are necessarily causes of technical debt, but they certainly correlate strongly with increases in technical debt. And there is sort of this uncanny correlation with deadline pressure. So what do we do to decrease technical debt? In traditional systems, well, we write tests. These might be unit tests or system tests or integration tests. We might refactor code. And by refactoring, I mean rewriting the same piece of code to do exactly the same thing, not increasing functionality, but making it cleaner, more readable, more maintainable, better abstractions, things like that. We might refactor at the system level. So take a whole bunch of spaghetti and turn it into a couple of nice servers that talk to each other through tighter APIs. We might create better abstractions and enforce tighter barriers. And we can increase readability in our code or systems, and we can increase the level of documentations. And these are all activities that, in my experience at least, correlate with a lack of deadline pressure to add new functionality. Right? This is not what you do when you're trying to roll out a new feature. This is what you do when you have a little bit of slack in your schedule and you can say, okay, how do we make our system better? And I see a sage nodding over there, which makes me really happy. Okay, so my argument for today is that machine learning systems have a special ability for increasing technical debt in systems. And I don't think that this was well appreciated a couple years ago. I've been beating this drum for a little bit, so you may be familiar with this now. But the argument basically hinges on the fact that machine learning systems have all of the problems of regular code-based systems, right? They're built of code, so if your code is bad, you're going to have technical debt. But there are also a wide range of machine learning specific issues that occur sort of at the systems level. You can sort of think new agey about the system level here. But the point here is that package level refactoring, just making your code better, is not sufficient for getting rid of all of the technical debt in your machine learning system. And in today's world, where we've got a number of fine sort of ML as a service platforms, simply using an ML as a service platform is not necessarily sufficient for getting rid of all of the technical debt in your machine learning systems. Okay, so how does this happen? Well, we think of sort of boundary erosion here. And by boundaries, I mean sort of boundaries in a system at the API level. When you think about it, a machine learning system is kind of a system you build when you don't know how to build something else that will solve your problem, right? In general, if we could solve a machine learning problem like computer vision by writing a bunch of well-formed if-then statements, we would totally do that because it's easier to reason about and easier to maintain. We don't do that in practice because we don't know how to write all those if-then statements. It's way too complicated. We can't wrap our heads around it. So instead, we punt the problem and say, OK, we're going to learn all of that logic through data. So we get a whole bunch of data, we mix it all together, and out comes some predictions. This means that, in general, it's not possible to make isolated changes. So if a machine learning model that, let's say, we've done for predicting food types is doing a bad job at predicting chocolate mousse, we have a bunch of ways that we might be able to improve the chocolate mousse predictions. We could maybe try some different regularization parameters. We could try adding another convolution in the network. We could maybe augment our chocolate mousse data. But there's no guarantee that it won't suddenly cause additional errors to creep up at some other part of the prediction stack. You know, maybe my chocolate mousse predictions get better, but maybe my chocolate malted soft drinks get worse. Right? This stuff happens. So I generally think of this principle that changing anything changes everything, which is sort of like the definition of high levels of system entanglement. And this applies not just to data, but it applies to sort of any part of your machine learning system. Okay, that's one. Another area that's sort of special about machine learning systems is the idea of feedback loops. So a lot of systems end up influencing their own training data. This could happen in kind of surprising ways. So I'm going to make up an example from the stock market prediction world because I do not work in this area and everything I say here is completely made up. That's a legal disclaimer. So you can imagine a world in which company A decides they're going to make a lot of money by learning on stock market data and using that information to buy and sell stocks. Okay? Over time, they get more data over time as yesterday's data comes in, and they use that to make predictions for today. Company B says, hey, that's a good idea. We're going to do the same thing with a slightly different model. Turns out company A's model has a bug in it, and they end up mistakenly buying way too much of a given stock. What happens to company B's model? They're like, whoa, awesome stock, let's buy, or maybe let's sell. But one way or the other, the bugs in company B's model is influencing the behavior of company A and vice versa, right? Which is totally weird from a system engineering standpoint. Not only do I have boundaries across pieces of code, I have boundaries being violated. I have boundaries being violated across different organizations potentially. And this can happen in sort of infinitely complex ways, because we are now saying artificial intelligence again as a community, and intelligent systems learn from the worlds around them. And this could happen suddenly. Maybe there's a bug that hits today. Maybe it happens gradually over time, where these two systems sort of balance out against each other and they drift off into some part of the space that's different than where we thought they would be. The gradual changes are the scary ones. These are really, really hard to detect or debug, and finding ways to give yourself a stable baseline over a long period of time is a super interesting data challenge. Okay, undeclared consumers. So let's say I've got a system that creates a prediction signal. Maybe it's a computer vision system, and it's figuring out what my food types are. Some downstream consumer might use that. Maybe there's an app that decides it's going to go ahead and use that as one of its inputs into doing menu recommendations. And obviously, I'm making this stuff up. Now, if I have a bug, or at least a inordinately high error rate in my chocolate mousse predictions, and I decide to fix that, right? I could sort of say, well, I'm making my model better. I'm going to fix my model. I'm going to roll out a new version of my model, and everything's better. Well, the app developer might have said, well, wait a minute, my app is great, but it does a bad job on chocolate mousse predictions. So when I see chocolate mousse stuff coming out, I'm going to multiply that one by a factor of 2 on my downstream end, right? So now what happens when I go ahead and roll out my fixed model? I break the app that's depending on it, right? If I don't know about all of the consumers of my model downstream, it's very hard for me to warn them or to verify that improvements to my model don't cause errors downstream. And so I view the number of undeclared consumers as a sort of key factor in thinking about how hard it's going to be to make improvements to a system. So then we think about data dependencies. And data dependencies is sort of the framing that I'm using for what we normally think of in machine learning land as features. So features are the things we put into our model that help it predict and help it learn. It might be the pixel values from an image. It might be various text strings that are extracted from a web page. In large part, the data that we give to a machine learning system acts in place of code. Right? We use the data that we train a model on to define its system behavior. So it's kind of like code, and that code also defines system behavior. If we add more features to a model, we're adding more data dependencies, which is kind of like adding more packages that you're depending on in traditional code, more imports. If I'm adding more imports and I'm not keeping track of which ones are stable, or how the versioning cycles are being done, or how those updates are being done, I'm exposing myself to risk, right? In the same way, if I'm just adding feature after feature to a model, I am potentially exposing myself to risk of instability. This can happen really easily, because as machine learning people, we like to increase the accuracy of our models, right? It makes us really happy to go from 99% to 99.2%. And sometimes you can get to 99 to 99.2 by adding one magic feature. But maybe you've been working on this model for 6 months, or maybe a lot of smart people have been working on this model for 2 years or 5 years. And it turns out the way that you get to your next 0.2% accuracy is by adding 10 features, each with a 0.02 benefit. Or maybe you just evaluated a whole bundle of features and said, hey, when I stick these 20 features in, I get this nice benefit. Yeah, let's just do it. That sort of feature bundling carries a pretty high cost. And that cost is that now your system is exposed to this additional set of dependencies that may break on you. And think about what happens when a feature breaks on you. Essentially, you are an undeclared consumer of the upstream producer of that signal. So it could break maybe by someone, quote unquote, improving it for you. Not necessarily your favorite day. It could break by maybe it stops being produced. It could break by maybe being just flat out inaccurate sometimes. So I think that it's really important to take care when we're adding features to a model to really balance not just what is the accuracy improvement that we're getting from them, but what is the incremental cost that's coming with them? Are they paying for themselves in terms of their long-term maintenance cost by the additional accuracy that we're getting? And in particular, this means that we have to be willing to forego sort of epsilon improvements in accuracy in order to save large amounts of maintenance cost over time. Okay, and then sort of a final one here. So I think call these correction cascades or calibration cascades. It's often sort of tempting that you've got a model that does well at one task. Maybe it's this food prediction thing that we've been talking about, and use it for an auxiliary task. We're going to use this model and make a slight tweak on top of it. Now it predicts drink type. Reasonable idea, and certainly a way to move much more quickly than building a whole new model from scratch. But again, we get into this sort of tight coupling situation where now it's no longer possible to make improvements to any one of those models in isolation. You can only improve them both together or evaluate them both together. So I would be wary of calibration cascades because it does sort of tend to calcify your systems. I have seen systems where there have been calibration layers that go 20 or 30 deep, and sort of the failure mode there is, and I see a look of shock and surprise, which is the appropriate reaction. But sort of what happens here is, okay, once you've got 10 calibration layers, you've got two choices. You can either add another one and pay a little bit more pain, or you can take the time to pay down all that debt now. And there are short-term, long-term factors, so I recommend thinking carefully before going down that path. Okay, so now let's talk about some other system-level considerations. So when I think about the cool part of ML, I think about, okay, let's make some algorithms, or okay, we're going to add in, attentional adversarial network recurrences, or who knows what, right? This is the sort of thing we write papers about. This is the sort of thing that we really enjoy doing. But when we talk about machine learning systems, there's a little bit more there, right? And in some sense, the writing model code or doing sort of the model tweaking is maybe 5% of the work, maybe 2% in that range. There are a lot of other pieces that need to be built. Now, obviously, in a world in which ML as a service platforms exist, part of the value proposition of those systems is, okay, we're going to take some number of these boxes and sort of do them for you, which makes perfect sense. But that doesn't mean that all of these boxes go away or that any external system is going to be able to do everything for you, especially in the areas of data collection, data preparation. So this often means that we end up in a glue code world in which to interface with some existing system. We write some code that's maybe not super high quality and maybe not even in the same language as the rest of the system, but it's a sort of like little ad hoc interface to get the data in the right format from system A to system B. This also means that we end up sometimes with what I call pipeline jungles, where our data preparation might take the form of a whole bunch of jobs. Maybe it's doing a set of joins. Maybe it's doing, calling out to a couple different servers, and then doing some verification and some cleaning before it gets sent out to what we hope is a cleaner system. So this is, again, another area where real care is needed. Bugs can creep in here super easily, and they can be almost impossible to detect downstream. Okay, so so much for all the good news. What are we going to do? So how do we handle a world in which we're building mission-critical systems that may be difficult to maintain over time? So I believe that testing is one effective, relatively unsexy strategy for working in this space. So when we're testing regular code, we write the code, we verify that it does what we want it to do, and then we send it off into the world to be a production running system. And what do we need to test? Well, we need to write unit tests that verify the expected behavior. We need to write integration tests to make sure that the thing that we put in place actually plays well with the rest of the components that it's working with. And then once it's off in the world and running, we need to add some monitoring to make sure that on a minute by minute or second by second thing that nothing's breaking. Just because it was working yesterday doesn't mean it's working today. So we want to make sure that monitoring is in place as well. So what happens with machine learning code? Well, we write the machine learning code, we verify its expected behavior, and that's just the thing that does sort of the math, right? Then we need to actually train a model and verify that our model is good, and then that's going to go off into the world and be a running system. But if we only worry about code and integration testing, we're kind of leaving a bunch of these boxes untested. So what else can we do here? We need to recognize that the data coming in here is one of the key vectors where things can go wrong. And we've put together a set of tests that we think of as a reasonable sort of standard, at least of things to consider. So this is we put together a rubric where we've got 4 categories of tests on machine learning infrastructure, sort of like the code that does the machine learning, the model development process, which is sort of this most scarily manual part of the whole stack, in my opinion. Tests for features and data that are coming in, and then tests that are ML specific for the monitoring of a running system. And this is in a paper that you can find online. But I'll go through just a couple of them to give you a sense of the flavor that we're talking about here. So for testing our ML infrastructure, one of the tests that we recommend, and we recommend 7 or 8, is that you want to test the models via a canary process before serving them in production. And what do we mean by that? Well, let's say you've got a model that's defined with, we'll call these TensorFlow ops just for the sake of argument. And we've got a couple ops here. I've got my circle op and my square ops. This is sort of pieces of code that are forming this model. And I send it off to a server. I've verified the model is good. Send it off to a server, and the server knows how to handle this model definition. And so it gets pinged for requests and issues predictions, maybe millions at a time, or who knows what. OK, so Wednesday comes along, and there's a new version of TensorFlow, or a new version of my package, or a new version of a given feature. It could be anything. And so I've replaced one of my squares with a little triangle here. And I'm going to send it off to my server. And the server says, what, triangle? I've never seen a triangle. So this is the sort of thing that can cause crashes. Crashes are the sorts of things that can cause a very bad day. And so we recommend to have a carefully defined canary process where you can detect these kinds of issues with very few queries before sending them off to wide production. Again, like not sexy, but yes, important. OK, here's another one. We want you to test that training and serving features compute the same values. What do I mean by that? Well, let's sort of imagine a system where we're training a model on some process that's coming in from logs. Maybe it's people who are taking photographs of their favorite food and labeling them for us or something like that. And then we're computing some feature from that. We're using that to train a model, and we look at our trained predictions and make sure that those all look good and on maybe some held.test data. And then we ship, once it looks good, we ship a version of that model off to serving, often to serving clusters in the world or maybe on people's phones or who knows what, and those get used for making live predictions from there. OK, so far so good, except that there's a slight wrinkle here, right? Because the data that gets used at inference time, when we're actually making the predictions, doesn't come from logged data, right? It comes from live data. It comes from what users are actually showing us, right? So maybe the data is coming in from some live server feed, or maybe from the user's phone, or who knows what. And there we need to create feature A as well and send it off to our little server to get the live predictions, right? Now, what happens when the code that produces the live version of the feature is different than the code that produces the logged version of the feature? This may be necessary, right? You may be talking with a logged file versus a camera, right? It's going to be different code. Well, it means that there's the opportunity for feature A to be defined differently at serving time and test time. Right? This is sort of the classic OMG moment when you have a bug that can be very, very difficult to find without going back to the root source and making sure that that your features have the same values when they're computed from the log data as they do when they're computed from the live data. One trick for this is you can log the values of the features that you're creating at serving time and then use that as a basis for comparison. Useful trick. Okay, so we recommend that you sort of put together a score for this, and we've got these 4 areas for ML testing, and we kind of think that the right thing to do is to take your minimum across these boxes and use that to judge the health of your system. So I think it's a useful paper. It's not going to grab any headlines, but I think it's a really useful set of best practices. So let me leave you with one more thought here. So this is a set of technology readiness levels from NASA. And NASA knows all about technology readiness levels because they want to make sure that their systems in production, such as rocket launches, go really, really well. Cost of failure is high. Now, we've been talking mostly about systems that are at this highest level, systems that are fully tested, that are launch worthy, all this stuff. What's interesting is that any given machine learning model might have pieces that are also maybe a little bit more under development. Right? The field is moving so fast that it's difficult for us to say things like, okay, don't use an attention network in this because we haven't had 10 years of experience with it in this setting, right? That's not going to happen. And in fact, I would argue that any real system probably has components of it that might be at every point in this set of readiness levels. We've got some pieces that are completely sort of research that maybe need to be evaluated in the same setting as the final production model, just because there's no other way to get the data set of that size or realistic evaluation. So I think this is a really interesting challenge, because we have to build systems that are robust enough to be able to handle the vagaries of research and the uncertainty about what's going to happen next in terms of the next developments that are going to occur. And this requires us to think really hard about our system design. I think it's just fascinating work, and it's a really neat time to be working in this field. So I'll leave you with that thought. I will give the obligatory mention that I'm at Google in Cambridge, which is just down the street, and that we're hiring. And with that, I will say thank you. Appreciate it.